Welcome back. I hope you enjoyed your lunch. And now we're going to get back to the presentations. And I think all our judges are here. I cannot see you guys, so whoever is not here, I see you. I see you, Louise. Thanks. But the next team to present their project is Team 1. And I assume Team 1 is here. All right, you guys can start. And you have 45 minutes, plus 5 minutes setup if you have the 7. Are you bringing your vehicle here? Oh, so it will be at the end, I suppose. Huh? Yeah. All right, please. Please give them a hand. You need more than one, or? Yeah. Just have to make sure it's working.
It will.
Huh?
I've talked to them.
Okay, good.
Yeah. All right, welcome back from lunch, everyone. Hope you enjoyed it. We are Team 1. Our agenda for today is going to consist of our presentation, of course, our target market, the vehicle itself, market research that we've done, our design, the engineering, and of course, last but not least, the manufacturing plan. Our team consists of, at this moment, Howard University, Monterrey Tech, Mexico City, Monterrey Tech, Monterrey, and McMaster University. Diego?
So this is the feedback from the last year, on 2017. There are some topics that we focus on according to the feedback from judges. The first one is the affordability of our product. You will see in the next slides that we are going to talk more about this. Also, a more detailed business plan and the manufacturing analysis. The main scope of design a self-power system vehicle is to give to the baby boomers first and last mile option to mobility. And also, our prototype is portable, easy to carry, and also is able to access easily to the public transportation. Now, Ruby is going to talk more about the baby boomers or final users.
So, as shown in 2016, North American citizens took 10.4 billion trips on public transportation, from which 69% of the users had to walk to and from their bus station or train station. But as my partner Diego already explained, the baby boomer generation may suffer from some mobility limitations, such as slow and limited mobility, and not so fast emergency response, resulting in 60% of these users fearing an accident when coming off or on a public transportation, even though these users still use public transportation because they find it more convenient and environmentally friendly. It's obvious this population is growing over the next years. Right now, the biggest population is located in the United States of America with 79.4 million. The second largest one is in Mexico with around 8 million, and the third one in Canada with 5 million. All this data according to a survey run in 2015. Numbers speak themselves. A new electric mobile market is growing, with e-bikes and electric scooters taking the lead right now. But they are not all user-friendly, as this revenue is expected to grow twice its size the market over the next 9 years, they still lack some features that are key important for baby boomers to take it as a first and last mile solution. So our team went out seeking for answers, and an extensive survey was run, in which we found that most baby boomers will be available to use our vehicle as long as it's not exceeded from 8 to 20 kilograms on carry-on weight. But what do we do to make our vehicle possible for all this baby boomer generation? My colleague right now is going to explain how we did it.
Yep. So before we begin, we'd like to show you basically a before and after picture of our design. So on the left, you can see our forum, our final forum design, which is the lacquers design. And based on the areas of improvement that my colleague Diego has said, we reiterated and redesigned, and we have finally arrived at the prototype on your right. So as you can see, it's a prototype diagram. You can see the seat, the rear suspension and brakes, the battery, the in-wheel hub motor, the front suspension, the controller, and the HMI, which is the human-machine interface. So just a little insight into how we kind of brought our design into our prototype is that we started from the ground up. We tackled what kind of road conditions, what kind of surface areas that our wheels would have to handle, and then from there we find what kind of rims that we would need to be able to build on top of those, and eventually we would just build all the way up to what we would have as our seat. So on the right, you can see the project requirements and design constraints as given to us by PACE. And so while we were designing our prototype, we did a trade study based on the currently available urban mobility devices on the market. And so after comparing various specifications, performance, and the price, we agreed on a target for most of our performance and prices. So as you see on the bottom, that's bolded. We're looking for a foldable, portable device that could reach 12 miles per hour, had a max range of 31 miles, 44 pounds in terms of weight, and it would be under $3,000 US. And so I'll pass it on to my colleague Ryan to talk about the front suspension.
So when dealing with front suspension, we had a few things to think about. Of course, we had weight, aesthetics, efficiency, serviceability, and we took all of these into account and weighted them, ranked them from 1 to 4, 4 being the best, 1 being the worst. And as you can see here, the telescopic front fork is 24, and linkage suspension is 23. So it was a close call, but we ended up going with the linkage suspension, or telescopic front fork suspension. This is the early CAD designs and drafts of the telescopic front fork suspension. Moving forward with this, we completed an FEA analysis with taking in dynamic load into account, a force of 2,500 newtons. Came out with a factor of safety of 3.58, which is pretty safe in my opinion, for a dynamic load coming off a curb. Here we have the front fork integration. Most front forks you'll find in the market today are tapered. They go from 1 1/8 inch all the way down to 1.5 inch. And now to talk about a rear suspension.
Okay, so what you're seeing it's the final design of our suspension, but obviously that design went from scratch to first prototype, second prototype, and then our final prototype, which is the one you're seeing on the main screen. So this design was inspired by a grasshopper leg. So what you can see is that the leg goes inward and the whole suspension is way, way tighter, and you can have a narrower wheelbase in your device.
Okay, so before selecting a battery for our mobility device, we have done a down selection of all the batteries that are being used currently that is available, that are being used in mobile devices. So we ranked them from 1 to 4, 1 being worst and 4 being the best. After ranking all the batteries, we have found that lithium-ion battery is the best to use for mobile devices because of their charging time and life expectancy. Where is that? Oh. So now we have, again, before selecting the battery, we have to look for the constraint given to us by PACE. So our battery has to last at least 31 miles, which is about 50 kilometers. And the life of the battery has to be about 1 year. And the charging time has to be between half an hour to 1 hour. And our preferred constraint, since our scope of the project is to fulfill first and last mile, and so we wanted to take that on consideration. The weight, we wanted to keep the battery as light as possible because we don't want our target users to carry such a large battery, heavy battery. Eventually, they have to replace it. We want the cost to be as minimum as possible, and we want to match the voltage of the battery the same with the motor. Little technical difficulty.
Next slide, please.
Okay, so this is our primary selected battery. As I said, lithium-ion battery is ranked higher than any other batteries, so we have selected lithium-ion battery. This battery with a single charge will last between 3 to 4 days, and the life cycle would be about 3 to 4 years. And so it is more preferable for baby boomers because we don't want the baby boomers to replace the battery once a year. That would be expensive. And the dimension of the battery is suitable with our device because the structure of our mobile device matches the structure of the dimension of the battery. So in order to fulfill the scope of the project, we need 2 of these batteries to go about 30 miles. Okay, so we have a fast charger for the primary battery along a standard charger that comes with the battery. So with the fast charger, our target user will be able to charge the battery within 1 to 1.5 hours. We have a secondary battery. This secondary battery is just for HMI. This secondary battery is not connected to the motor. Again, going back, we have 2 batteries. The primary battery is going to be used for the motor, and the secondary battery will be only used for HMI. So just like we did a trade study for batteries, we have done a similar study with the motor. So we looked at all the motors that are currently available that are being used for mobile devices. So the wattage of this motor ranges from 250 wattage to 500 wattage. And all the motors have wattage below 400 can't carry our target user who's weigh more than 200 pounds. So we don't want to be limited with only 200 pounds. So we are going with higher wattage from 400 and above. Next slide. Now my colleague JP will talk about more about battery and which battery we need to use for our mobile devices.
Well, we divided the existing motors into categories, the external electric motor and the in-wheel hub motor. We compared them in a scale from 1 to 5, 5 being the best and 1 being the worst. We went with the in-wheel hub motor since it's twice as good as the external electric motor. For the motor, we bought it in a kit, which is the most affordable option since it already comes with a controller, a throttle, and a brake, which we changed. It's important to notice that our motor is a 36 volt, which is, our motor is a 36 volt operated, so it complies to our battery requirements. These are the hard constraints that were given by PACE, with the max size from the front and rear wheels being from 12 to 12.5 inch, that they should be lightweight, and the weight distribution should be 40% to the front and 60% to the rear. We complied to these ones being, the front wheel, actually it came with the motor, and it was exactly the size that we needed. It's 12.5 inch in diameter. It's pneumatic, and well, it works with the motor. It's placed outside the motor. The rear wheels are also 12-inch standard bicycles, which all of these are off-the-shelf products. So for the affordability, it's better for replacements in case of puncture or any other accident. I'm proceeding with my friend Miguel.
So we tried to be as down to earth as possible as we could. So we thought about everything, and we thought also about the economy of the end user. And we realized that by grabbing components off the shelf, like an engine, or like a motor, or a seat, or some other parts, we were able to reduce manufacturing costs by quite a big margin. So for the seat, we went for a boat seat. Those seats are designed to be really comfortable for long periods of time, and they are they are really affordable. That's why we choose it. So as you can see, our main structure is made out of aluminum. Out of aluminum sheets. Aluminum sheets were cutted and then coated on a water jet, and then assembled and welded together. So what you're seeing is actually an early stage model. What we are going to bring next in the next few minutes is going to be like the operating model. So we also added an HMI, which is a human-machine interface. We decided to go as simple as possible. We didn't want to make an app that includes way too much stuff, because those are, they are not complicated, but they are more, it's a steeper learning curve in order to use the device. So we went for a simple design on the HMI. And next. And we succeeded at that. Our main user interface is so simple that when tested, 93% of people were able to use it correctly on their first try, which is something that not every application or adult is going to be able to do on an app.
So here we have the rear brakes that we decided to go with. We decided to choose a mechanical road disc brake, something that's really popular and common on bikes existing on the market, ready to go. It's adjustable, simple to use, simple to install, simple to set up, simple to tune if need be. Compared to other types of brakes, it's very compact and lightweight, which is what we're trying to achieve with our device. Versus other mechanical brake systems, we've noticed that the rotor and disc brake, the disc brake and caliper setup has better braking performance. So in an experiment to try and confirm what we assumed, we pretty much had set up a test to determine the maximum grip force strength required and the output stopping force. So our findings were about 50 newtons of grip force would result in about 180 newtons of stopping force. This translates to about 6.5 meters of stopping distance at full load from top speed. Here we have the initial, very early on adaptations of brake mounts and integration. This did not consider any suspension, so prior to the judges' feedback, we just had a simple design to add the brakes, or to mount the brakes to our device. As you can see with the yellow bracket, we tried to keep simplicity in mind, so in the sense that when it needs to be serviced, it can be done so independently and quickly. Moving on, we have the early adaptation with suspension. This suspension that was initially chosen was based on the ICE recumbent bikes, simply because it seemed to suit our device needs. However, due to the complexity of this, the idea was shortly abandoned after. The second iteration of rear suspensions, we kind of went with the wishbone setup, a double wishbone setup. However, as you can see from the diagrams, in order to mount the brakes, we needed to use some sort of backing plate or hub. This proved to be a bit clunky and counterintuitive in design, something we weren't really looking for, so as well this idea got scrapped. Finally, we come to the final design that we decided to, the current setup. As you can see, the rear brakes are mounted in 2 locations, strategically so that there's equal braking on either side. Here we have the rotors actually attached to the axle, whereas the calipers are attached to the device themselves. Further considerations we had were to have a handle, a brake lever that was ergonomic, so comfort was in mind for the user and the target audience. Another consideration we had is a doubler device for dual actuations. Since we decided to use 2 rear brakes to kind of to prohibit brake steering, we decided to use a single actuator to then, in turn, brake both calipers. I'll now be passing it back to Alvin to just summarize the engineering design.
Thank you. So right here is our total bill of materials. As you can see, we had a target of around $3,000, as stated before. And so by choosing all of our cost-efficient and affordable options, we managed to lower it down to $2,285 USD. So now I'll be passing it on to Diego to talk about the technical design of the HMI.
For the HMI, we used a Raspberry Pi, and we were able to connect a touch screen to the Raspberry, and also to be able to control lights and a horn. We are using relays to be able to control with 3 volts output of the Raspberry, 12 volts lights and horns of our product. We are also using a DC-DC converter to decrease the voltage to 5 volts in order to power the Raspberry Pi. Now, Sigifredo will talk about the manufacturing design.
Thank you, Diego. Well, that's true, I cannot see you. Well, first, as my partner Diego already told you, the internal HMI diagram corresponds to the design for manufacturing and design and assembly. And then we can move on to the Technomatics plant, designing in Technomatics. Basically, it consists of 2 assembly lines. This is the upper line, which consists of the main structure, and runs simultaneously with the HMI creation that takes place in this line. So first, we got the raw material here, that's aluminum planks. And then from here, it goes through a water cutter. And then it depends if the piece needs to go through the bend station or directly to the weld station. So once the central piece is done, here we can add the battery, the case battery, sensors, all stuff. At here, we have our first quality checkpoint. And then we can move on to, with the help of this KUKA arm robot, we can place the seats on the main structure. But remember, here is our HMI being installed. The HMI process consists of a plastic injection mold here. And then it goes through this, the second station of the HMI consists of, well, here we can install the screen, the buttons, and all the embedded system. For security of the plant, we place another quality checkpoint. So that's the first one. Here's the second one, and everything is going well. Here we can put them together. So after that, we can place the paint, and also here's another robot to place the wheels. Finally, we have the electronic and electric test right here. And also we have the test road, this one. So then we can move on to the, hold on. What's happening? Yeah, next slide, please. Right there. This is the same as before. This is only a flow manufacturing process made in Visio. But the thing here is that it splits the process into three processes, like this, the HMI process, general process, and electronic and circuitry process. Then, next slide, please. I'm going to talk to you about the business model canvas. So who are our customers? The customers, the end user is actually the persons who are running North America. Baby boomers are here in Mexico, US, and Canada are who run the economy. So, and also a possible customer is the Generation X. So the value propositions, I'm going to stay in aligned to what my partners already told you. That is fast charging, the long-term battery. Then I can move on to the channels. Here we are trying to get the business-to-business market, also business-to-customers market, and also with the retail and wholesale stores. What about the customer relationships? We are trying to get to our customers through the customer service, warranties. Also, we are trying to make a final disposal battery plan, and obviously the maintenance of the equipment. Then, what about the incomes? Obviously, we are trying to get money from the sales, from spare parts, and also for the maintenance. Now, my partner Ruby is going to continue with the business canvas.
So all these value propositions and customer relationship lack of sense if we don't have key activities to approach our final user. So what do? We are planning on making available for this generation to have a test ride, as it is shown that baby boomers like to test the vehicles that they are buying and the products they are willing to spend money on it. So we have to make a special marketing generational for these final users. Our key resources for that are the acquisition of components such as the batteries and electric motors for final disposal, the spare part sales, and the workshop for maintenance to keep a happy customer along through this period of acquiring our vehicle. Our key partners, of course, have to be the suppliers of our main components, like the motor suppliers and the screen suppliers, which we don't plan to manufacture our own. But we have to keep also good alliances with our physical retail stores, as we have to have happy customers and happy workers and happy partners. So our cost structure is everything that we have already explained that has our vehicle and comes from the suppliers and the office rent and the warehouse and everything that needs to be in order to keep a good business. What about the sales forecast? We have planned a 4-year sales forecast to be increasing over the months, being the first 3 months the toughest one with a very high injection of money to start a normal business. For example, this sales forecast is projected to be for the next 4 years, and it's based on the automobile behavior running in the United States in 2017. As you can see, on August being our first month, as if we started the business right now, we have a very strong budget to keep because we have to buy office equipment, we have to pay workers, we have to educate the workers to work, machinery, and we have to start paying rent for whatever warehouse or plant we're planning on building. Over the course of the months, we are planning to start selling our vehicle at a regular price of $1,577, starting as a startup. But over the months and the years period, the sales will be flowing differently according to the holidays, as normally people tend to buy more during special holidays like Black Friday or December, special holidays where they can sell more like a normal business. Right now, I'm going to pass the microphone to my partner, Ryan.
So in conclusion, we've looked over specifications, target market preferences, foldability, efficiency, and cost, as well as what it's going to take this thing to market, what it's going to take to maintain it over the years with manufacturing and other maintenance issues. And we have this product here that we're going to be showing you as it rolls out. And it's running, something we haven't seen yet today. Thank you all.
Tomorrow is going to be a surprise about LEDs and stuff. So, thank you. Thank you.
Thank you, guys. Please give them a hand. Yeah, you're right. We have a working model. You're going to leave it here? No. For me? For me? Hi, I'm your customer. and the track. I would love to test it in the track. Okay. Wait for you. Does it have a reverse? Does it have a reverse? No. Okay. All right, thank you, guys.